Another constant we'll be talking about is Ka and also pKa. We've talked about how pH is a measure of the environment of an aqueous solution, the amount of protons, the amount of H plus in a solution. We can also talk about equilibrium constant of acids themselves. So again, not how the acid is affecting water, but the acid itself. The strength of the acid, or the ability of the acid to dissociate, is called its Ka. It's dissociation constant. So this is measuring how well an acid does its job at being an acid, essentially, at dissociating and giving away the protons. So acids that dissociate very well are usually strong acids. And they tend to, of course, have low pHs. And acids that do not dissociate very well in water are weak acids. These will not have as low pHs. The dissociation constant is an equilibrium constant for an acid is expressed in this way. Your particular acid, which we will denote as HA, is a common form, is the acid in its undissociated form. This normal HA goes to or dissociates into a proton, H plus, and this A minus is what we call the conjugate base. Essentially, what is left over of the acid once its proton has dissociated. And the dissociation constant, this number constant, is found again by setting up a normal equilibrium equation where we have our products, concentration of products per concentration of the acid. So in this case, it's going to be the concentration of the H plus times the concentration of the conjugate acid, A minus, divided by the concentration of the non-dissociated acid, HA. So here you can see that if you have a lot, if you dissociate very well, right, this number will be very high. You'll get a lot of H plus. And so the lesser value of Ka, the weaker the acid, or vice versa. The bigger the Ka, stronger the acid. Okay? Now, just like with pH, because these numbers tend to be concentration numbers that are either very large or very small, so we're using significant figures in 10 to the negative and 10 to the positive 14, etc. We're going to use log to talk more simply about our Ka. In this case, pKa is equal to the negative log of the Ka. So just like with our pH, here we can talk about pKa, negative log of pKa. And just like with pH, it's going to have a reverse trend. So the bigger the Ka, as we just said, big Ka means that you have a strong acid. And this also means that your pKa is strong. Again, opposite trend, just like with pH. So for a weak acid, for example, your Ka will be lower. This is your weak acid. And that means your pKa will actually be larger. Now this is a constant, as I said, so the ability for something to dissociate, the ability for an acid to dissociate is constant. It always dissociates to the same extent. And so this is constant for any conjugate acid and conjugate base. So any pair has this constant Ka and also pKa. You can look these up. You can also calculate them just based on observance. But again, these are all constant terms. And most biological compounds are actually going to be weak acids or weak bases. We're going to be looking more into the Ka and pKa when we are involved with a weak acid, weak base conjugate pair. So thinking on what we just spoke about, this question is posed. Does a strong acid have a greater or lesser tendency to lose its protons than a weak acid? Well, just in the name, a strong acid is better at donating its H+. So it actually is better at dissociating than a weak acid. So it has a greater tendency to lose a proton than a weak acid. So based on that, does a strong acid have a higher or lower Ka than a weak acid? And again, we can think about this just in the terms of what Ka means. Ka is equal to concentration of the product, H plus and A minus, over concentration of the acid. We just said strong acids are better at going this way. They're better at dissociating. They're better at making H plus. That means that this number on top is going to be bigger than the number on bottom. And so Ka will be higher. So stronger acids have a higher Ka than weaker acids. The stronger acids have a higher or lower pKa than weaker acids. Now remember that pKa is the negative log of the Ka. And because of this negative log function, we see the opposite trend. And so we have a big Ka, as is shown, we're going to have a low pKa. So strong acids have a lower pKa. So to just visualize this on a chart, here are some pKa's of different molecules, and also the appropriate pH at the bottom scale at which they dissociate. So here's a scale of pH, and here is the pKa of the actual compound. So pKa can be thought of, the reason the scale is useful, the reason we talk using pKa, because the pKa number is going to give you a general idea of the pH at which the acid is going to dissociate from it. And so, again, when you have a pKa that is small, as we just said back here, small pKa's are for strong bases, and high pKa's are for, low pKa's are for strong acids, as shown in this question, talking about strong acids. And and large pKa's are for weak acids. And this kind of pairs up with the trend of pH. So a strong acid has a low pKa associates at the lower pH. Here's an example of a strong acid, phosphoric acid. And you can see that it has a low pKa and a stronger acid, and it dissociates around the pH of 2.14. Here are some other examples. So the ammonium ion, shown here, NH4+, has a pKa of 9.25. This is a much weaker acid. And you can see along the pH scale that needs to dissociate closer to this basic range, 9.25. Now, some acids can have multiple protons that they dissociate. This is called being diprotic or triprotic, meaning you can have 2 or 3 protons that you ultimately dissociate. And these dissociations usually get harder. Once an acid dissociates 1 proton, it's harder to get it to dissociate the second or third proton. And that's reflected, for example, let's look at phosphoric acid again. Phosphoric acid, H3PO4, has 3 protons that are able to dissociate. And each of those protons have respective pKa. So this pKa is showing the constant at which the conjugate base from the previous reaction will leave its proton. So here you can see H3PO4 losing its first proton. This has a very low pKa. It will dissociate at a low pH. This is a stronger acid. It's a very strong acid when in this form dissociating its first proton. Now, the ability of H2PO4 at the conjugate base from our prior reaction to dissociate its next proton is going to happen in a little bit more basic range. Its pKa is around 6.86. And even further, if you want to try to dissociate that very last proton off from this conjugate base, its pKa is 12.4. Again, way further in this basic range. Now let's talk a lot about the pKa constant. Again, the constant talking about how an acid helps it dissociate and the concentration to which it dissociates into H plus and its conjugate base. And we've also talked about pH, or the measure of H plus in an aqueous solution. These two are very interrelated because acids release protons, release H plus, right? Yes, look at their Ka. An acid dissociates to form H plus, and that H plus will then shift the balance of an aqueous solution of water, changing the pH. Very naturally, these two things are related. And I'm not going to go through the whole derivation of how pKa and pH are related, but ultimately, we can use this equation, the Henderson-Hasselbalch equation, to show the relationship between pH and pKa. And that relationship is as shown. The pH of a solution is equal to the pKa plus the log of the concentration, remember again, this means conjugate base, the concentration of the conjugate base and conjugate are usually the starting acid. Okay, so this interrelates a lot of things, and we're really going to be focused on Henderson-Hausdorff equation. You can derive a lot of information from it. For example, if you know the pH of the solution and you know how much of each of the concentration of conjugate acid and conjugate base are present, you can derive the pKa. The thing that is most often calculated is, since the pKa is a constant, we know the pKa of some type of acid, and we know how much conjugate acid and conjugate base we put into the solution. We can calculate what the end pH should be. Or vice versa. What if we know we want our pH to be 6? Well, then, if we know what our starting acid we're going to use is, we know it's pKa, since that's a constant. So if we want something to be pH 6, then we can calculate what ratio of H of conjugate base and conjugate acid should be mixed together to get pH that we need. Again, this equation is very flexible and it allows for calculating a myriad of things in different situations. So let's try it out. Let's try a sample question here. If we have a solution that is comprised of 0.1 molar acetic acid, we know acetic acid, that's what's in vinegar, by the way, we know its pKa is 4.76. And the solution also has a concentration of 0.05 molar sodium acetate. So then what is the final pH of the solution? First of all, I'm going to write the Henderson-Hausdorff equation out. We know how to relate things like pH, pKa, and concentration to this equation. So pH equals pKa plus the log of the concentration of the conjugate base over conjugate acid. And if you want to write this, for example, to help you remember, you want to write this as like concentration of B over concentration of A. I've also seen it written that way. That's fine. Whatever helps you remember what goes where. Okay, so we can probably look at this quickly and figure out a lot of information. We know what the pKa is, right? We know we have to find the pH, so that's what we're looking for. We also have two concentrations here. But how are they related to this conjugate acid and conjugate base? Well, we have to think about, in this case, acetic acid and sodium acetate, what the acid and the conjugate base are in the formula. So acetic acid, CH3COOH, you can see it still has its hydrogen attached here, is the acid itself, kind of given away by its name. And acids dissociate into, remember, a proton, an H plus, and everything that's left over. So what's left over? CH3COO minus, that's our A minus. So the acetic acid component is here. That is our CH3COOH, and that is 0.1 molar. Now, sodium acetate. What the heck is the sodium ion doing in here, and how is it related? Well, we're mixing things together, and unfortunately, ions like this don't really exist that we can handle outside of being dissolved in a solution. So if you wanted to have a solid form of this ion, you could make it a salt. So you could make CH3COO minus with a little sodium plus there. That forms a salt. Those are two ions held together by ionic bonds. But ultimately, we're just using this as a way to put CH3COO minus into a solution. When you see these ion bonds, sodium is usually there, or you'll sometimes see potassium. That gets used as an ionic counter ion, just kind of to hold a place so that we can form a physical salt of that particular conjugate base. So this sodium acetate is the form, the salt form of our conjugate base, and it is 0.05 molar. Okay, so that means we do have everything here. We want to find pH. We know pKa and we know our concentration. Let's plug it in. Our pKa is 4.76. The concentration of our conjugate base is 0.05. And the concentration of our conjugate acid is 0.1. Okay? So after I do this calculation, we're going to get a final pH of 4.45. Again, just to kind of work it out, show you what is going on here. 0.05 divided by 0.1 is going to be 0.5, taking the log of that and adding it 4.76. So the log of 0.5, then doing log of 0.5 is negative 0.30. And we're adding this to 4.76. So it's the same thing. 4.76 minus 0.30. And that equals what I've calculated here are 4.45. 4.46, 4.45. Okay, so now let's practice a little bit with the Henderson-Hasselbalch equation. We've talked about generally what pH is, how to calculate pH, what pKa is, what it means about an acid, and how to use pH and pKa to get information about concentration. Now let's talk about the idea of a buffer. Buffers are just a solution that mixes a weak acid and its conjugate base together. And in fact, in this last example, testing out the Henderson-Hasselbalch equation, this was a buffer. We had a weak acid, acetic acid, and we had its conjugate base, sodium acetate.